Okay, YouTube, so now I am going to start a lecture on how to properly draw Lewis structures. So I just want to give a lead off here and state that this can be an area that many general chemistry students will struggle in. Until you learn to follow the proper setup and rules, you will have a lot of difficulty drawing proper Lewis structures. Now, if you follow the set of rules that I show you here, it is usually easy to master the basic structures. When you start getting to some of the more complicated organic structures, those can take some more patience and practice before you're going to master those. But the goal should be, if you're just starting out, to master simplistic molecules like water, carbon dioxide, ozone, things like that, the nitrate ion, before you start getting to how do I draw the Lewis structure for, parachlorobenzene or something like that. That would be a very complicated structure, paradichlorobenzene, in comparison to some of those others that I just stated. So let's get started here in terms of how to draw a good Lewis structure. Now, I'm going to run through one example as I'm going through these rules, and that will be the length of the video. I will open up another video after this that is going to have several different structures that you can practice along with me. But watch this video first to completion to make sure you understand how we accomplish this, okay? So, number one, the first rule, I'll let you know you have to have a little bit of background in electronegativity and understand the periodic trends across the periodic table. So for electronegativity, we go to the bottom left corner of the table and we find the highest value up in the upper right, and that excludes the noble gases. So the halogen fluorine holds the highest electronegativity value, and then the metals on the bottom left corner of the chart hold the lowest electronegativity values. That's the general trend that we find. So in terms of electronegativity, we will always place the least electronegative atom at the center, and that will exclude hydrogen. So hydrogens may be less electronegative than some of your other atoms, but we never place hydrogens in the center because when we have a hydrogen, hydrogens can only form one bond. So they would make very poor candidates for center atoms, which is why we always exclude them from this rule when we're trying to predict. Now, in general, the elements that have very high electronegativities also have what's known as a lot of non-bonding pairs or lone pairs around them. And those pairs sort of just sit and increase electron density around that atom without getting involved in bonds very often. I don't want to say never. You can have non-bonding pairs in a organic reaction that then reach out and all of a sudden are involved in a bond later on. Okay? However, the least electronegative atom that you come up with is going to be the one that has the potential for the most bonding, the most unpaired electrons. So for instance, the very basic structure of carbon on a Lewis scale has 4 unpaired electrons, whereas the very basic structure of oxygen on a Lewis dot scale would have 2 pairs and then 2 available for bonds. So if I can only form a maximum of 2 bonds to that oxygen, where I could form 4 bonds on this carbon, it would be ideal to put the carbon at the center of the molecule, not the oxygen, because it has the most branching points. Now, it turns out, if you follow the periodic table, the electronegativity trend, that it would be increasing going this way. So there would really be a nitrogen, right, an oxygen, a fluorine. So carbon is less electronegative than oxygen. So in a substance, let's say carbon dioxide, which is the example we're going to use here, in a substance like carbon dioxide, I expect to find carbon at the middle, and that's because it is the least electronegative atom. So that is step one. We always want to find the least electronegative atom, excluding hydrogen, and place that at the center of the atom. I'm sorry, at the center of the molecule. Okay, so coming down here, we're going to work on this and say, here's carbon, and that's going to be the center to my carbon dioxide. So step 2, what do I do now? Draw single bonds to all the outer atoms. All right, that's not hard. So carbon is the center atom. I need a single bond to an oxygen and a single bond to another oxygen. So that should take care of that. Now I need to sum up the valence electron pool. So when we deal with Lewis structures, we only show the valence electrons because those are the electrons involved in bonding. So they are the only electrons we're concerned with when we get ready to start showing how a structure comes together as far as its bonds. So the valence electron pool, which I'm going to keep over here, you need to simply sum up the total number of valence electrons available to you, and that's your electron pool. So carbon would normally have 4 valence electrons. If you think about, it's got the 1s shell, that would have 2 electrons, and then that shell becomes the inner shell. The outer shell, or the valence shell, is now the 2s and the 2p, right? So carbon has, if you count along the periodic table, you get 4 electrons there. So using the same general logic, we can get 6 electrons per oxygen. Now I have 2 of those, so the total there is going to be 12 electrons from the oxygen. So I want to add my 4 electrons and my 12 electrons. I get a total of 16 electrons that I can utilize in creating this structure. That's what that means, right? Now every bond is represented with a line, and that bond is 2 electrons. So when I get ready to work with this, I would say, well, I already have 1 bond here and another bond here, right? So that's a total of 4 electrons that I've already taken up. So now this number, if I take that back down, would go to 12 electrons that are left to utilize. You have to keep track of your valence electrons. You can't go past the 0 mark. Okay, so now that I have a good tracking on my electrons, number 2 and number 3 are both done. So now I'm going to fulfill the valence shells of the outer atoms. You always start with the outer atoms as you're working on this, not the inner. So in order to do that, I'm going to start creating pairs until I have a total that would fulfill the valence set. So oxygen is going to need 8 electrons to get to the noble gas state to fulfill its valence shell. Turns out most of these compounds we're going to be working with are going to need 8, except for hydrogen, which will be an exception. That's going to be a duet. It will only need 2. So if hydrogen is involved in a single bond, that is enough to fulfill its valence shell. So the oxygen here, each oxygen only has 2. So we would need to place 3 pairs of non-bonding electrons around them. And at that point, I've now fulfilled them because I see I've got 8 electrons total here, and I've got 8 electrons total here. Remember that I'm getting 2 electrons from the bond, right? And then I'm getting 6 electrons from the non-bonding pairs. So the total of 8 per oxygen works out there. And I've now completed number 4. I've filled the valence shell. I have fulfilled the valence shell of the outer atoms. So I need to keep track of my electrons, like I just stated. So I come down here and I say, here's 2, 4, 6, and then 8, right? So if I'm going to do that, I'm going to do that twice because I've done it on each side of the molecule. Now remember, we already counted these bonds, so it's really the lone pairs that we just used up, right? So it's 2, 4, 6, because I already counted both of these bonds when I took the 4 electrons away from here. So just keep that in mind, that when you are working with sort of your electron accounting or bookkeeping, that you don't double count. So if I've got 6 electrons I put around the oxygen here and another 6 here as lone pairs, then 6 times 2 is 12, so I've used up all the rest of the valence electrons. I don't have any more left in my pool. Well, the oxygens are satisfied here, but then if we go to step 5, we have to look at fulfilling the valence shell of the inner atom with leftover electrons if available. Well, there are none available. We just used up the rest of them, so we're now at 0 electrons. I don't have any extras to sort of populate or give lone pairs to my carbon here. So how many does my carbon have? It's got 1 bond and 2 bonds. So that's a total of 4 electrons. Carbon's going to need 8 electrons. So I need to find a way to get 4 electrons to that carbon so that its valence shell can be satisfied. Now if I had electrons left in my electron pool right here, well, that would be fine. I wouldn't have an issue at all with that, because then I could just take those and populate them to the carbon. But in this case I don't have any, so I go to step 6. I need to fulfill the valence shell of the inner atom with double or triple bonds. So how does this work? Well, it turns out if you're out of electrons in your valence pool and you need to fulfill the central atom, you are permitted to take electrons from the non-bonding pairs and dump them in order to create a bond. So think about it. If I get 2 electrons per bond and carbon already had 4, I need to do this 2 times. I would not create a triple bond with one oxygen and keep another one at a single bond. I would expect them both to donate equally. They both have the same electronegativity. And it turns out, we're going to have another lecture on formal charge in a little bit, but it turns out that the structure where one oxygen has 3 bonds and the other only has 1 is going to add some unneeded charges to the molecule, which is going to be destabilizing. So it turns out that the final structure of carbon dioxide is going to have a double bond. Now this double bond comes from the lone pairs of electrons. Okay, so this set of non-bonding electrons, and the term lone pair is used interchangeably with non-bonding electrons, and this set, they both got dumped in to create new bonds, and now everything has a fulfilled valence shell because the oxygen here has 2, 4, 6, 8. The carbon, if you look at its bonds, it's got 4 from this double bond and 4 from this double bond, and then again this oxygen would have 2, 4, 6, 8 due to the double bond. So the proper structure of carbon dioxide would be like this as far as a Lewis structure is concerned. All right? Now this doesn't talk about molecular geometry, it doesn't talk about hybridization or any of that stuff, so this is going to be an ongoing series that will help cover that. But the first thing you need to get down is how to create the proper Lewis structures. So hopefully everybody found this lecture useful. Please remember to like, comment, and subscribe as it greatly helps the channel. You can check out our courses over at Udemy if you feel like you'd like to support the channel. I've got a link for that in the description. And other than that, I will see you guys for the continued lectures so that we can master how to draw Lewis structures together. Thanks for learning with us, and I'll see you next time.